Hello, Professor Lee. Can you hear me?
Don't worry. And the camera also.
So share.
Yeah, don't worry. The camera.
Dear colleagues, today we start the final day of our international workshop. And the first lecturer today is Professor Kyun Lee from Chungnam National University with his third lecture on dynamical system from measured theoretical viewpoint. Please note that can you write the questions and I'll read them to the lecturer at the end of the lecture. Professor Lee, you are welcome.
Thank you for the introduction. Hello, everyone. In my final lecture, I will talk about recent trends in dynamical systems from measured theoretical viewpoint. In my second lecture, I talked about what is a differentiable dynamical systems and the dynamics of hyperbolic systems, especially about the structural stability and dynamics of Smith's horseshoe. And finally, I talked about the applications of Zaphe-Infante equations. The main goal of the theory of dynamical systems is to understand the long-time behavior of the orbit of the system in topological point of view, or differential, or geometric point of view, or measured theoretical point of view, and the numerical point of view, and the statistical point of view. Today, let me talk about dynamical system from measured theoretical point of view. Okay, let me start with the Smith's spectral decomposition theorems. If a flow phi is an axiom A flow on a compact smooth manifold, axiom A implies the non-wandering set omega of phi is equal to the cross of the periodic set of phi, and the set is hyperbolic. Hyperbolic means it has the decomposed by stable space and the unstable space and the flow line space, one-dimensional space. In the stable space, if you take a vector, then the norm of the vector goes to 0. And if you take a vector in an unstable space, as time goes to infinity, the norm of the vector increasing. In the case, Smith proved that the flow has the spectral decomposition. It means non-wandering set is decomposed by finite union of disjoint closed invariant set, such that the flow is topologically transitive on each omega I. It is very famous and important and fundamental theorems in differential dynamical systems. Okay, for a moment, let me talk about the novelty of the theorems, spectral decomposition theorem. We know that for any point x in M, the limit set, omega limit set, and the alpha limit set belong to here. At the beginning, I mentioned that the goal of dynamical system is to understand the long-time behavior of the orbit. So long-time behavior, that is omega limit set and the alpha limit set, belong to non-wandering set. So we see that we see that the complicated phenomena of the system occurs within non-wandering set. But the theorem says here topologically transitive means there is a dense orbit. There is an orbit in omega I which is dense in here. So in some sense, each omega I can be expressed, approximated by one orbit. So roughly speaking, Smale's spectral decomposition theorem implies non-ordering set omega of phi can be expressed a finite number, can be approximated by finite number of orbit, because each omega I is topologically transitive. So afterwards, there are many works that generalize the Smale's spectral decomposition theorem to more general setting. As the first topological extension, the Aoki and Komuro in 1984 proved that if a flow on a compact metric space is expansive and has the shadowing property on its chain recurrence set, then it has the spectral decomposition. It is a topological extension done by Aoki and Komuro. One of the recent topics in the theory of dynamical system is to understand the structure of topological or differentiable dynamical systems from major theoretical viewpoint. This is different with the ergodic theory. In ergodic theory, we wanted to understand the structure of the major preserving map on the major space. But here, we want to understand the structure of the long-time behavior from major theoretical viewpoint. First, we are going to present measurable version of the Smale's spectral decomposition theorem. Okay, before that, in the theory of dynamical systems, a lot of vocabularies. Among them, we have expansiveness, shadowing, or topologically stable, structurally stable, chain recurrent, or transitive, etc. This kind of concept, in a sense, metric version. Already we know that expansiveness, shadowing property, or topological stability, or structural stability. We can think about this kind of concept from major theoretical viewpoint. So first, I will introduce the notion of expansivity from major theoretical viewpoint. Of course, the other concept also we can generalize. But only for the expansiveness, first, I am going to extend the concept from major theoretical viewpoint. Okay. For this, let us recall the concept of expansiveness for flows. We say that a flow is expansive implies for any epsilon there is delta such that dynamic delta is contained in orbit arc, one orbit arc. Already I explained what is dynamical delta ball. So expansive means dynamic delta ball is contained in one orbit arc. So what is dynamic delta ball? Okay, here is the orbit of x, then y. Through the y orbit go together, but ignoring the speed, then we say that x, y, z belong to dynamic delta ball. So it is not expansive, because in the case of expansive, if x and y are different, then the orbit must go outside of the delta ball. The notion of expansiveness by Bowen and Walter has a weak point. More precisely, if a flow is expansive, then every singularity of the flow is isolated. It is clear because if x dot is a singularity of the flow and c is a continuous function, constant function, then we know that dynamic delta ball of phi at the singularity is the ball, just the delta neighborhood of the singularity. We can check clearly, easily. By definition of the expansiveness by Bowen and Walter, dynamic delta ball must belong to the epsilon arc through the point x dot. But x dot is a singularity, so it is x. So it means delta neighborhood of x dot is only x dot. So every singularity is isolated. Hence, every expansive flow on a compact manifold does not admit a singularity. So in the theory of differential dynamical system, in the flow case, diffeomorphism case is slightly different. In the flow case, if the system is expansive, then there is no singularity on the manifold. This is one of the weak points, in my opinion. And Ruggiero introduced another slightly extended concept, all expansiveness. That is, dynamic delta ball is contained the whole orbit, not orbit arc. Slightly generalization. Of course, there is a counterexample. Based on this concept, 2014, Carrasco, Oliveira, and Morales introduced the following concept of measure expansiveness from the measure theoretical viewpoint. I just put the CM because we are going to introduce another concept of expansiveness based on the measure. So I put the name, C, Carrasco Oliveira is a family name, CM, measure expanse. If there is delta for any M of X is the set of all Borel probability measures with the C weak start topology. So for any Borel probability measure with orbit shadowing, what is the meaning of this one? Orbit shadowing means measure of the orbit is equal to 0. This is corresponding to the non-atomic measure in discrete case. Non-atomic measure means one point of the measure is equal to 0. So in the discrete dynamical system, the orbit is the countable set, countable union of the point. So in the non-atomic measure, orbit of the discrete dynamical system should be 0. So in the flow case, we can introduce that kind of concept with the orbit shadowing, orbit vanishing. So orbit vanishing measure is corresponding to the non-atomic measure for the discrete dynamical systems. So for orbit vanishing measure, if the measure of the dynamic delta is equal to 0 for every point in phase space, then they call that is measure expansive, CM measure expansive. Here, M of X denotes a set of Borel probability measures on X with weak start topology. We proved that with my student, we checked a flow is a CM measure expansive if and only if it is countably expansive. Countably expansive means dynamic delta ball is contained in a countable union of orbit. What is expansive? Expansive means dynamic delta ball is contained in the orbit arc. Orbit arc. In the case of R expansive, dynamic delta is contained in whole orbit, only one orbit. So we can give the name. Two expansive means dynamic delta is contained in two orbit, contained in there. Countable expansive means dynamic delta is contained in the countable union of orbit. So more general. Of course, there is a counterexample. Clearly, one expansive implies two expansive, but the converse is not true. So we knew that a flow is a CM major expansive, it is countably expansive. But still, every CM major expansive flow on the compact manifold also does not admit a singularity. I'm going to tell you the reason quickly. Let phi be a CM major expansive flow on a compact manifold, and suppose the flow has the singularity x dot. Then by definition, in the case of singularity, if x star is a singularity, then the dynamic delta bar is equal to delta neighborhood of the x dot. By the definition of CM major expansivity for any vanishing, orbit vanishing measure, mu of the dynamic delta bar, this is dynamic delta bar, should be 0. But if mu is a Lebesgue measure on the manifold, then that is an orbit vanishing measure. So for the Lebesgue measure, delta bar over x star should be 0. This is a contradiction in the manifold. So we can see that still Carrasco, Oliveira, and Morris major expansive concept on the compact manifold does not admit a singularity. Okay, yeah, dynamic delta bar is equal to 0. Then we say that major expansive. So at the beginning, I mentioned about Smale's spectral decomposition theorem. And many people try to extend the theorem to more general setting. So we can think about it. We knew that Japanese people, Nobuo Aoki and Komuro, proved that if a flow is expansive and shadowing, then it admits a spectral decomposition. So we have a natural question is slightly CM, major expansive is a more general concept than expansive. Under this assumption, the system admits a spectral decomposition or not. But we can see that in the following example, CM major expansive flow with the shadowing property does not admit a spectral decomposition. Let me give you an example. Sigma 2 is the set of two symbols and the shift map sigma. Then we know that for each natural number, we can choose a period point with the period. And we are going to put E equal to union over orbit of Pn. And take a copy F of E, which is disjoint with the sigma 2, and we write X equal to union of sigma 2 union F. And give a matrix on the space here, such that is compact, is a homomorphism. This idea, this model is introduced by Carvalho and Cordero, 16. Let me give you a detail there. Okay, here, P2 is a period point with the period 2. So sigma P2 and here. P3 is P3 here, sigma P2. And after second, sigma 2 of P3, period 3. and the Pn is the period n. Copy and put here. This is the space. But here we have the matrix on sigma 2. We know the matrix, but here there is no matrix. I'm going to give the matrix. How? If you take a point in here, in the green, in F, if you take a 2 point, we have the corresponding 2 point. For example, the distance between 2 point and this one, there is a corresponding to here. That is corresponding to here. So we have the distance here. Distance plus 1/2 plus 1/3. Between this point and this point, for example, we can lift this point, corresponding point. So 1/n plus the distance between 2 points. If we give the distance on the set X in this way, this is the formal description of the matrix, then we know that that is a compact matrix space. And of course, the dynamics, here is the dynamics on here. Here, every point is periodic. So we have the dynamics. This is the discrete dynamical systems on compact matrix space. So we consider suspension flow. Because we are talking about the continuous flow, suspension flow, then the flow, we can prove that that is a CM measure expansive. Also has the shadowing property. We can show that. But we are going to prove that the suspension flow does not admit a spectral decomposition. To get the contradiction, we suppose that the flow, I'm sorry, this is Pf, suspension flow. Suspension flow has a spectral decomposition here. I'm sorry, this is phi of omega of Pf, also suspension flow. Suspension flow phi has a spectral decomposition. That is decomposed by finite union of basic set. Omega is a basic set. It is topologically transitive. This is finite. Non-ordering set. Every periodic orbit belongs to here. So we can see at least one basic set contains infinitely many periodic orbits. In green colored periodic orbit, green color, you can imagine this is the copy in F, which are opening here, phase space. This contradicts because of the transitivity. We know that on omega I, its suspension flow is transitive because we assumed that it has the spectral decomposition theorem, the spectral decomposition. So we can see that the flow constructed in this way by suspension flow does not admit the spectral decomposition. So here we introduce another concept of expansiveness from the meta-theoretical viewpoint. We say that a flow P is measure expansive. Nguyen is one of my graduate students. Noctang Nguyen is one of my graduate students. With me, we introduced, it is published in Journal of Differentiation. A flow P is measure expansive if there is delta, such that for any Borel probability measure of the dynamic delta ball minus orbit is equal to 0 for every x in x. Slightly different with the CM measure expansive. One more definition is, we say that phi is invariant measure expansive if there is delta such that for every phi invariant measure, here for every Borel probability measure of this set is equal to 0. But here, only for the phi invariant measure. Measure of the set is equal to 0. In this case, we say that a flow phi is said to be invariant measure expansive. You know, clearly expansive means measure expansive because dynamic data must belong to the orbit. So this is empty set if it's expansive. So empty set of the measure is 0 for every probability measure. So it is clear. Measure expansive implies invariant measure expansive, also clear by definition. This one is for every measure should be 0. This is only for the invariant measure should be 0. So we are going to give the previous example shows that invariant measure expansive does not converge is not true. And we are going to give an example. Measure expansive converge is not true. So we are concerned about this concept, invariant measure expansive. Our concern is this concept. So the novelty of the concept is invariant measure expansive flow on a compact manifold can admit non-isolated singularity. In the vector field dynamics or dynamics on the manifold, singularity is arrays is a problem. Near the singularity, there is a very complicated phenomena. So it is not easy to control the singularity, understand the dynamics neighborhood of singularity, because hyperbolic set do not contain a singularity. Hyperbolic set do not contain a singularity. Because of continuity of the splitting, continuous splitting, it does not contain a singularity. But this definition contains a non-isolated singularity. Let me give you a very simple example. Consider flow on the unit sphere given by this vector field. So this one. P is north pole is a source, and south pole Q is a sink. P. Then we see that this flow is invariant measure expansive. Of course, this is not, there is no expansive flow on the sphere, but this is invariant measure expansive. Let us check quickly. Okay, this is a set of invariant. For any phi invariant measure, we know that support of mu is contained in only 2 points. So we know that the set of all invariant measure, phi invariant measure on the sphere is a linear combination of the Dirac measures. For any phi invariant measure in here, measure of the dynamic delta ball minus orbit is clearly 0 for every point. Very simple example. This means that phi is invariant measure expansive. So this is invariant measure expansive. This example is invariant measure expansive, but non-measure expansive. You can check this one. I'm going to give an example, measure expansive, but not expansive. For this, for any natural number, and in n, let an be a 2 point. 2 point set. A1 is 2 point, A2 is 2 point, An is 2 point, which are disjoint. And the distance of the set and the point go to 0 on the Hausdorff matrix. And they are denoted by x equal minus n to n product an. This one union, this is x-axis z product 0 union image. 1 point compactification of the plane. This is a sphere. And consider the homeomorphism given by the following shift map. So this is A2, capital A2. So minus 2, minus 1, 0, 1, 2 product A2. This one is minus n plus 1, blah, 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 0, 1, and n product an. But the distance between 2 points, close and close, goes to 0. And finally, in the axis, x-axis, every natural number, the integers. And the homeomorphism is, okay, this is x, all this set is x. And that's, dynamics this one, this point moved to here, moved to here, moved to here, moved to here, this point, moved to here, and again, and again, again, and again, this point moved here. So it is periodic. In the same way, this point moved to here, again, this point moved to here, in this way, and the x-axis moved to right side. We consider suspension flow of this one. Suspension of this one. This is measure expansive, but it is not expansive. This model is introduced by Artig, but we consider the suspension flow of this one. So the suspension flow is measure expansive, but we can easily see that the suspension flow is not expansive. So we prove that by definition, expansive implies measure expansive implies invariant measure expansive. But the converse is not true in general for flow case. Finally, we proved that is a measurable version of the spectral decomposition theorem. With my student Ngoc-Thang Nguyen, we proved this one. What is the if a flow is invariant measure expansive and has the shadowing property on the chain recurrence set, then it has the spectral decomposition. So non-wandering set is decomposed by finite disjoint union of invariant set, which is topologically transitive. So in other words, non-wandering set can be approximated by finite number of orbits. Here, one orbit can be approximated in here. One orbit inside can be approximated. So non-wandering set can be approximated by finite number of orbits. To prove this one, we use the extension theorem first. This is also interesting. To prove the spectral measurable version of the spectral decomposition theorem, we needed this kind of this extension theorem. It means if a flow is invariant measure expansive only on chain recurrence set. Only on chain recurrence set means pointed chain recurrent point means the pseudo orbit, pseudo solution, numerical solution. There is a periodic numerical solution. The set of chain recurrent point is this one. If is invariant measure expansive on here, then we can extend it is invariant measure expansive on the whole space. But we can construct a flow which is invariant measure expansive on non-wandering set. Non-wandering set, but not invariant measure expansive on whole space. So in the case of non-wandering set, cannot be extended to the whole space. First, let me introduce a simple example such that Phi is invariant measure expansive on non-ordinary set, but it is not invariant measure expansive on the whole space. Give you a simple example. For the natural number, Sn is the circle centered at 0,1 over n, the plane with the radius 1 over n, and let x be the union of these circles, S1, S2, Sn, and let phi be the flow on the space, satisfying. Have a singularity is 0, only one singularity on the origin, and omega limit set, and alpha. Omega limit set is a positive limit set in a sense, and the alpha limit set is a negative limit set. Is only 0 point for every point in here. Then we see that phi is invariant measure expansive on here. It is clear, but it is not invariant measure expansive on the whole space. Let us check quickly. To show this, xn equal to 0.2 over n for its natural number, then for any delta, we can find a sufficiently large n with dynamic delta ball contains 0. Then we can see that Dirac measure of this one of dynamic delta ball minus orbit is positive. So contradiction. Because to be a invariant measure expansion for Dirac measure is invariant measure, of course. For every invariant measure of the dynamic delta minus orbit should be 0, but this is not. So this example shows that it is invariant measure expansive on non-ordinary set, but it is not invariant measure expansive of whole space here. X1, X2, X3, something like that. This actually is a singularity. Okay, let me give you an application of the extension theorem before we prove that to differential dynamical systems. And be a compact smooth manifold, the set of C1 vector field on the manifold using C1 topology. This is the without singularity and the flow. We say that a flow is a C1 stably invariant measure expansive. If there is a C1 neighborhood of this one such that perturbed system is invariant measure expansive. So system P is stable invariant measure expansive implies under small perturbation. Small perturbation, C1 perturbation here. Still, that is invariant measure expansive. In this case, we say that P is invariant measure expansive. With this terminology, we proved that a flow is C1 in stably invariant measure expansive if and only if it is omega stable. Why is the application? It is well known that a flow is C1 stably expansive. C1 stably expansive. Then that is quasi-Anosov. It is proved by Manne for the case of diffeomorphism. Also flow case by 3 guys later proved that. But here, so C1 stably invariant measure expansive implies omega stable is okay. But converse, we should use have to use the extension theorem because it is omega stable. Then we know that axiom A and no cycle condition. Axiom A means chain recurrence set is expansive, so it is invariant measure expansive. By our extension theorem, we see that P is C1 stably measure expansive on whole space. Similarly, we can prove that C1 generically flow is invariant measure expansive, then that is omega stable. Invariant measure expansive on whole space, whole manifold. So finally, let me introduce the relationship among the various expansiveness. Expansive by Bowen and Walter implies R expansive by Ruggiero, and implies the two expansive. Two expansive means in dynamic delta ball is contained in the two orbit, not one orbit. R expansive means dynamic delta ball is contained in one orbit. And similarly, we can introduce countably expansive. And we proved that R expansive is equivalent to our measure expansive. And the countable expansive is equivalent to the CM measure expansive. Also, we can introduce the invariant measure expansive. The converse is not true, of course. Also here, we can introduce invariant CM measure expansive. The relationship, the application of the differential dynamical system, we can introduce C1 stably measure expansive. Here, C1 stably CM measure expansive. The equivalent whole quasi-Zanosov. Also, C1 invariant, they are equivalent to omega stable. So we have this kind of diagram for the various concept of expansiveness. Of course, we can introduce the notion of measure shadowing or measure topologically stable. But here, I will not mention about the kind of concept. By now, I introduced dynamical system from measure theoretical viewpoint, especially focus on the expansiveness. Okay, finally, let me introduce two papers related to my third lectures. First one is a joint work with Carlos Morales from Federal University of Rio de Janeiro and San Martin in UCN University in Chile. And the second paper is a joint work with one of my students, Ngoc Thang Nguyen. Okay. This is the end of my talk. I was very glad to join this workshop and happy to meet all of you by online. Thank you very much again for joining to my series of lectures for 3 days. I hope to see you again. Thank you.
Thank you very much, Professor Lee, for your lecture. And we have a question for you from our audience. Could you please remind what the shift map does in your notation?
Yes. If I can use the blackboard, it's more easier to the please wait for a moment. Where is the example? Okay, here. Okay, yes. So sigma 2 is the set of two symbols, product of Z with the product of produce. So it is compact, but we can give the matrix on here. So two sequence x0, x1, x2, xn, y0, yn, y2, yn. The distance between two sequences in a finite block is important. We can give the matrix which produce the product approach. So we can give the matrix between two sequences. And the shift map means if there is if x is in here, x can be denoted by x minus 1, x0, x1, x2, x3. Then shift map means by sigma x left shift. So sigma of x equal to the base point is x1, left shift, moving to shift. That is shift map. Then that is a homomorphism. And it is well known that is expansive and the shadowing property. Also, for every n, there is a period point whose period is equal to n. And so yesterday in my lecture, Steve Smale used the shift map to understand the dynamics of the horseshoe. To understand the dynamics of horseshoe, he used the symbolic dynamics, like this kind of a shift map. Okay, any other question?
Thank you very much. No, there are no questions for now. I guess that's all.
Okay, thank you very much, everyone.
Thank you very much, Professor Lee, for your participation in our workshop.
Yeah, goodbye. Thank you.
Dear colleagues, we continue the online international workshop, and our next lecture is Professor of Rudan University Galina Lazareva. She will continue her mini course Mathematical Modeling of Compressible Fluids. Professor Lazareva, you are welcome.
Hello. My name is Galina Lazareva. I am professor in Rudan University. And today I will tell you about numerical methods for hyperbolic equations. Now, excuse me, I'll have to turn off the video camera to make the sound, my sound better. Thank you. Here in the slide shows the most understandable Russian books on this topic. And in this lecture, we will consider the basics of numerical methods for solving initial boundary value problems for hyperbolic equations. Why hyperbolic? Because the gas dynamics equations are hyperbolic type equations. The system of gas dynamics equations describes the flow of compressible medium. And now we consider theoretical issues related to the study of only finite difference schemes. As examples, the solution for the shallow water model and finite difference schemes for solving the linear advection equation will be considered. We will consider also dissipation and dispersion. Let's learn how to predict the properties of the solution of difference equations. Next slide. Let's consider the Cauchy problem for a linear system of first-order differential equations. Here, U dimensional vector function of variables x and t. It is space and t it is time. A is a real matrix with elements A sub I, G. A system of equations is hyperbolic in some domain of variables x, xt if each point of this domain is eigenvalues lambda sub 1, lambda sub 2, lambda m. For the matrix A are real and distinct. The integral curve x sub k of t of an orderly differential equation is called the k characteristic of the system of equations. It is assumed that the elements of the matrix A smoothness sufficient for a single characteristic corresponding to the eigenvalue lambda k to pass through each point of the plane xt. Characteristics drawn through the point xt, where t is positive, it is time, in the decreasing direction of time t, with intersect the O x-axis at m different points. Eigenvalues of the hyperbolic system, and using x sub L, x sub R, we denote the segment of the O x-axis bounded by the intersection points of this axis with the m and first characteristics. The domain of dependence of a point xt for a system of equations is the set of points of the upper half plane bounded by the extreme characteristics x sub m and x sub L. And the segment x sub L and x sub R. The dependency area of the point xt is shown in the figure. The solution of the system at the point xt will depend only on the values of U sub 0 of x on the segment this segment from x sub L to Rx sub R. Therefore, the initial data outside this segment is changed to other data, and the solution at the point xt will not change. The area of influence of a point x sub 0 is the set of points ext of the upper half plane bounded by the extreme characteristic of the system coming out of this point ex sub 0. So characteristic corresponding to the eigenvalues lambda sub L and lambda sub m. The area of influence of the point x sub 0 is shown in this figure. If the initial data is changed only at the point x sub 0, then the solution of the hyperbolic system will change only in these points. Now let's assume that instead of the Cauchy problem, we need to solve the initial boundary value problem on the segment from 0 to 1. Then, in addition of the initial conditions, you must set boundary conditions. The number of boundary conditions on each of the borders is determined by the number of characteristics entering the area. For example, if m sub 0 is eigenvalues of lambda sub k are positive for x equal to 0, then you need to set m sub 0 boundary conditions on this border. If on the boundary x is equal to 1, the number of negative eigenvalues is m sub L, and therefore exactly m sub L of characteristic enters the region through the right body, then excuse me. Then a set of boundary conditions must be set at this boundary. Since the eigenvalues depend on time, the number of H conditions on each of the borders may change over time. It is a very interesting fact. Let us now consider a gamma homogeneous hyperbolic system of equations with constant coefficients. For a constant matrix A, its eigenvectors and eigenvalues are constant, so they don't depend on X and T. Let L sub K be the K left eigenvector of the matrix A, corresponding to its eigenvalue lambda sub K. And then we can multiply the system, our system, on the left by this vector. The solution of S sub K from of x t of the equation is carried along the characteristic without change. How we get S sub K? We rewritten our equation such way, then we get S sub K, and so we get Riemann invariance S sub K, and we can say that S sub K of xt is carried along the characteristic without change, and is therefore calculated it for all times by the initial value of S sub K at the intersection of the K characteristic with the OS X axis. Now let's look at the very simple example. It is the simplest mathematical model that can describe the movement of a liquid without surface waves in the linear model of shallow water. Look at the figure. That is the model of shallow water, and these equations is the model of shallow water. Here, nu of xt is the elevation of the liquid surface about undisturbed level. Here we see undisturbed level, and our nu xt is the elevation of the liquid surface. Another variable is u. This is nu in our equations. This is u. U of xt is the velocity of the liquid, and n sub 0 of x new sub 0 of x and u sub 0 of x is the elevation and velocity at the initial time. Time is equal to 0. And h sub 0 is a constant. It is the depth of our pool. G, what is G? H sub 0 is the depth, and G is also constant. It is the acceleration of free fall. And this system of equations can be written as a homogeneous system with a matrix A and the solution vector U. This is our solution vector U. The matrix A has two different real eigenvalues, lambda sub 1 and lambda sub 2. So this our system of equations is hyperbolic type system. The characteristic equations take the following form. This is the characteristic equation. Therefore, the characteristic are straight lines. You can see. And characteristic passing through a point xt intersect the OX axis at points x sub L and x sub R. This characteristic passing through a points on the OX axis in these points. So we have the matrix A with two different eigenvalues. The left eigenvalue of the matrix A corresponding to the eigenvalues given before. This one. The relationship between the Riemann invariants R, which equal to S1, and S, which equal to S2, and the original dependent variables is given by these formulas. From these two formulas, we obtain these formulas for solving the Cauchy problem in invariants. How we get it? We take these formulas here and we get this. Finally, we
Professor Lazareva, I'm sorry, could you repeat the last sentence, last thought?
In this slide, okay?
Yeah, Yes.
Finally, we get an exact solution to the Cauchy problem. Nu xt is the elevation of the liquid surface above the undisturbed level. U xt is the velocity of the liquid. So we have found an exact solution of the Cauchy problem, elevation and velocity. This is our exact solution. And now we need to set a boundary condition. When solving the initial boundary value problem under consideration, one condition must be set at each end of the segment from 0 to 1. Are impermeable to the liquid, which means that the velocity of the liquid on these walls, this is velocity on the walls here and here, is equal to 0. And now we see the final mathematical formulation of the problem of the movement of a liquid with surface waves in a limited pool. Our pool is limited. This is our area. This is our problem. Here we see closed domain. And we see boundary conditions here and initial conditions here, and our equations of hyperbolic type. We were able to find the solution to the problem analytically. It is the exact solution of our problem. The analytical solution can only be found in the case of linear coefficients. Here we have linear coefficients. The depth of our pool is constant in this case, so we can get this exact solution. If the coefficients are non-linear, then this problem must be solved numerically. The numerical solution is difficult for a shallow water model. So now let's look at the simplest example when we have to solve the problem numerically. But now we want to have a short rest. What is modeling? The model is the result of a collaboration between mathematical scientists and the experimental scientists. The algorithm is the result of the work of a computer scientist. The program is the result of the work of a computer scientist and programmer. There is an anecdote that any program has at least 2 errors. A very important part of mathematical modeling is proving that the model, algorithm, and program work correctly. And now let's go back to our lecture. Now we are discussing the basics of numerical methods for solving initial boundary value problems for hyperbolic type equations. So if our matrix A of linear hyperbolic system of equations is constant, then such a system can be reduced to a system of equations in Riemann invariance. In this case, the equations for Riemann invariance don't depend on each other, and each of them has the form like this equation. This equation is the simplest hyperbolic equation, and we call it the linear advection equation. This equation have constant coefficient, but this coefficient can be variable, for example. This equation can be used to study the properties of different schemes used for solving hyperbolic systems of equations. I know that our gas dynamic equations are the system of hyperbolic type equations. So it is topic for our mini course. Consider the Cauchy problem. This is our Cauchy problem for our advection equation. Characteristic x t is very simple. You see that is it is a straight line with the slope to the t-axis. Yes. Therefore, the exact solution of the Cauchy problem is determined by the formula O of xt is equal to O sub 0 of x minus at. The graph of the exact solution at time t is obtained by transferring the graph of the initial function to the value at. So we called this equation advection. Then for this equation with constant coefficient a, it's easy to write out an exact solution for the initial boundary value. For example, a is constant, is a positive constant. Then the following initial condition boundary value problem will be correct. It is easy to sub 0 of x and mu sub 0 of x of t sub 0 0 sub 0 of x and mu sub 0 of t, if these are differentiable functions, then the solution of the problem is defined by this formula. This is the formula for exact solution for this initial boundary value. Then we can get explicit finite difference upwind scheme, and let's discuss what an explicit upwind scheme is. Let us now proceed to the study of finite difference schemes for solving the linear convergence equation. Let's start with an explicit scheme with counter flow at wind difference for the initial boundary value problem. Everywhere else, we will consider only uniform meshes covering a closed region where t is from 0 t big T and x is from 0 to L. We construct the following difference scheme approximating the problem with first order. The name upwind scheme is related to the fact that if we consider the advection equation as a model equation for a system of equations describing the flow of a liquid or gas and identify the coefficient with the velocity of the liquid, then for a positive velocity with a positive a, the scheme takes the left difference derivative using the node x sub j minus 1 located against flow, so located upwind. Now we introduce uniform norms in the space of grid function. Space of right hand parts f sub h. The maximum principle can be used the following statement, and we have theorem that fulfillment of this condition a tau divide h less or equal 1 is sufficient for the stability of the upwind scheme in a uniform norm. And now I can answer a question. There was a question at the last lecture yesterday that I didn't understand very well because English is not my native language, and sometimes I find it difficult to understand complex sentences. Now it is possible to answer the question about the spaces in which the solution is being thought. What can I say about this? We are looking for a solution using finite difference methods. Therefore, the speed of convergence of the numerical solution to the exact solution is very important for us. This speed must be consistent with the smoothness of the desired solution, of the exact solution. We look for solutions to the equations of compressible media in the space of continuous functions. In the if the solution is discontinuous, such as shock waves, then we can only talk about generalized solutions. But it is about finite difference methods, particles methods, finite element methods, and finite volume methods work in functional spaces in all cases. This is proof of my theory. And then next theorem proving the condition. This is proof about this is proof first was the sufficient and this is necessary this condition for the upwind scheme for the stability of the upwind. Now we what we can do if our coefficient A is negative. If we take our scheme, we can see that it is absolutely unstable. And what can we do if A is negative? We can get the scheme like this. Here we go to the left in our indexes in space, and this is the condition of stability of this upwind scheme. It is also upwind scheme. So the next step, we have constructed two conditionally stable explicit schemes with anti-flow differences for the advection equation, and we get one scheme, and this is this scheme is stable with the following condition. Then we can take the explicit upwind scheme. It looks the same in the case of an alternating coefficient A from of xt. This is not constant, our coefficient A. For example, if the condition at A of 0 t is positive, and at LT is negative, then we met at the boundaries the segment 0 L, then we get the following upwind scheme, which approximates with first order the initial boundary value like this, and using the maximum principle, it can be proved that the stability of this scheme with variable coefficient is sufficient to satisfy the condition. This is our condition. Along with the advection equation, consider two more equations. I have 5 minutes, so I go to the end of my presentation. I want to say I have two equations. Here we see derivative xxx and derivative xx, and we can say that this derivative is tell us about dispersion, and this derivative tell us about dissipation. And now I want to show it in the graph here. Just a minute. Here we see that if we analyze the scheme for this equation, we can see that the scheme has dissipation. We can analyze it before we do our calculation, and we can see that our decision will be with dissipation of our solution. This is exact solution, and this numerical solution. And here we see dissipation. And other we can get another scheme, so-called Lax-Vendrov scheme, and here we can see we can see another effects at our solution. We can see that this is exact solution dashed lines, and our numerical solution can oscillate. This is oscillation. Thus, after analyzing the scheme, you can predict the behavior solution before you calculate. And everything that has been told now for the transport equation is used in the calculations of gas dynamic equations. That's all. Thank you for your our group. We will work together. Come to my lecture after the break, and I will tell you how you can predict the result of a galaxy collision using mathematics. Thank you.
Professor Lazarus, thank you for the interesting lecture. And we have some questions. The first one is the shallow water model related to the compressible liquid model?
Shallow model is another system of equations. This system of equations not take into account compressible. It is only very clear and very simple model of hyperbolic equations.
Okay, thank you. And the next question, if I understood it correctly, then it means the following. What restrictions are imposed on the elements of the matrix A capital?
Just a minute.
I suppose it is, yeah, no, on the above slides. Yeah, here.
Here. Так. Ой-ой-ой. Matrix A, in this case, it is a matrix M to M, and in this case, it consists of elements A sub I G. These elements are real, and these elements are constants, and A must be English. This matrix that from A is not equal to 0. I don't know how to say it in English. And it must be in Russian самосопряженный, yes? So I can't say it in English. It is difficult for me to answer in English. Excuse me. Kita?
I'm sorry, yeah. Самосопряженный means in English self-adjoint. Yeah, So thank you for your lecture and answers. We are looking forward to your next lecture, and the break is announced until 12 a.m. in Moscow time. Thank you.
Thank you.
Dear colleagues, we continue the online international workshop and we continue the mini course of the previous lecture. Professor Lazareva, you are welcome.
Let's continue my mini course. Third lecture focuses on the application of our equations. Then I stop my video camera. Okay. Okay. In mathematical modeling, we can build a model based on ongoing or planned experiments. We can also build a model based on observed natural phenomena. What natural phenomena can be modeled? There are many models of predicting whether the spread of industrial emissions in the atmosphere and in the ocean. There are models of natural disasters, volcanic eruptions, earthquakes, and tsunami. This is seismic sea waves. Models of mineral deposits are of great practical importance. There are studies that try to find answers to global questions about the origin of the universe and humanity. And I have some experience in modeling processes that are described by systems of gas dynamics. Some success using finite difference schemes and particle methods. And I have a lot of experience in modeling various dynamic processes in a continuous environment. It can be a gas, a liquid, or plasma. Such models require the creation of cost-effective algorithms. It is often easy to come up with an algorithm that solves the problem, but if the algorithm is too slow, it is returned for revision. Since the exact speed of the algorithm depends on where the algorithm is run, as well as the implementation details, computer specialists usually talk about the execution time relative to the input data. For example, if the input consists of n integers, the algorithm can have a runtime proportional to n squared. This means that if you run the algorithm implementation on a computer with an input size of n, it will take c must multiply to n square seconds, where c is some constant that doesn't change with the input size. Software testing is carried out using standard test sets. Thorough tests are required for gas dynamic problems. Also, we can find configuration of rotating self-gravitational gas. And then we use a comparison the solution of our system with the solution of a very simple system of equations. I show it to you in this lecture. If a model based on experiments, then software testing can use the prototype with known characteristics. Such tasks require calculations on supercomputer, and there are very interesting applications of gas dynamic equations in astrophysics. In this lecture, you will learn the model of the central collision of two galaxies. Also, we see numerical methods of hydrodynamics, verification, and parallel implementation. This project had three motivations: physics, supercomputers, and design concept. Professor Alexander Tutukov from INASAN from Moscow said the movement of galaxies in dense clusters turns the collisions of galaxies into an important evolutionary factor. It is a very important evolutionary factor because during the Hubble time, an ordinary galaxy may suffer up to 10 collisions with the galaxies of its cluster. Observational and theoretical study of interacting galaxies is an indispensable method for understanding their properties and a collision may result in the destruction of the galaxies, their coalesces, the conservation of the stellar components, and the destruction of gas components or their conservation of the stellar components with the formation of a new galaxy from their gas components. The gas component plays a major role in the scenario of the collision. Thus, it is necessary to simulate the collision of galaxies by means of the hydrodynamical approach. Let us consider the formulation of the main problem. The model is based on the solution of the gas dynamic equations, supplemented by the equation for gas inner energy and the Poisson equation. A Poisson equation for the gravitational potential. And here we see the cooling function. The equations of gas dynamics describe the movement of gas in a gravitational field. The change in the gravitational field is described by the Poisson equation. The stellar component of the galaxies is simulated by the central body that brings its contribution to the common value of the potential to this equation. Now I tell you in detail about each equation. The continuity equation is the differential form of the law of conservation of mass. Here, rho is density, v is velocity, v is from 3 components. This equation expresses the fact that the change of density over time occurs only from the transfer of density at some speed in space. Then the momentum equation, here you see rho is density, v is velocity vector, but rho multiplied by v is impulse. Phi is the gravitational potential. Next equation, total energy equation. Excuse me. Total energy equation. Big E is total energy. Rho multiply E is the speed. This is pressure, and this is potential, and this is cooling function. The cooling function is the heat sink, and phi is the gravitational potential. Here we can see that phi is, we can calculate phi from the Poisson equation. We calculate the distribution of the gravitational potential in space at each moment of time. To do this, we need to know the distribution of gas density, rho, in space. And we know this distribution as a result of solving the continuity equation and all our gas dynamic system equations. Such a complex system can't be solved analytically. It should be noted that the gas dynamic equations are a system of hyperbolic equations, and the Poisson equation is an elliptic equation, and we solve system of equations of different types, and it is a particularly complex task. Then the internal energy equation and the equation of state. We see here internal energy epsilon, and the internal energy is related to the pressure through the equation of state, which for an ideal gas can be written like this. Pressure is equal to rho epsilon multiplied gamma minus 1, where gamma is adiabatic coefficient, adiabatic index, and a total system of equations is ill-posed. It allows us to describe a gravitational instability of astrophysical processes. The boundary conditions. Boundary conditions are set for the system of gas dynamic equations. It is a Riemann boundary condition for gas dynamics, and Dirichlet boundary conditions for the Poisson equation. The problem is solved in cubic area in Cartesian coordinates on an uniform grid. And here the figure shows the computational domain, this is blue, and the initial distribution of gas. Here we see only one area with gas, and here we see two areas with gas. Blue is the computational domain. Yellow is initial distribution of gas, and orange is central bodies. Here we can see distribution of central bodies at initial time. At time is equal to 0. The stellar component of the galaxies is simulated by this central body. At the initial time, two disks are set to move towards each other. Disks have a mass. The disks are surrounded by gas. The gas is distributed evenly inside these two poles. The picture above shows mass distribution of the distributions of the gravitational potential. In classical mechanics, the gravitational potential is at location is equal to the work energy transferred per unit mass that would be needed to move an object to that location from a fixed reference location. It is analogous to the electric potential, with mass playing the role of charge. The reference location where the potential is 0 is by convention infinitely far away from any mass, resulting in a negative potential at any finite distance. Here in this figure you see gravitational potential for uniform spherical body. The purpose is to simulate the collision of the gas components of two similar disk galaxies. The collision is of central type along the polar direction. First, gas is the half of all mass, and star component is another half of mass. The gravitational field is determined by the behavior of not the gas component only, but also the movement of the star component in the disk part of the galaxy. In the model under consideration, the star component is a matter moving with constant velocity, only in this model. The density of this matter is not computed, but its mass, being equal to the mass of gas, brings its portion to the gravitational field. Is in such a way the star component interacts with the gas component only through gravity. My movies don't work now, excuse me. As a result of the simulation, the main scenarios of collision of galaxies were obtained. So I show you these pictures. Okay. A visible and theoretical research of a galaxy interaction is an irreplaceable method of their properties and evolution analysis. We have result of these collisions. A galaxy destruction, their junction, a conservation of star components, and the destruction of gas ones, or a conservation of star components with the creation of a new galaxy from their gas components. Here we can see it. Here we can see these scenarios, two galaxies, and we get 4 scenarios. And here, this picture, we can see how how two galaxies can create a new daughter galaxy. And then two galaxies go away from our domain, and we see only one daughter galaxies. Okay. If the relative velocities are small, both the galaxies and their gas components merge. If velocity greater than 500 kilometers per second, then the gas spreads to the intergalactic space, filling it with heavy elements produced by the supernova of the cooling galaxies. If velocities are large, then the massive star components flow through each other almost free, leaving the gas components to slow down and heated by the collision. Here we have two galaxies, and after collisions we have also two galaxies. If the common gas component of the colliding galaxies has enough time to cool down to the virial temperature during the time of collision, then we can get a new galaxy emerges. So we at initial time we have 2 galaxies, and then we have 3 galaxies. Here film. In addition to this model, location of central bodies and gas distribution, you can set any other parameters. Galaxies can have different masses, you see, and collide at different angles, like this. This slide shows 4 main areas of calculations that are currently being performed based on the basic model of galaxy collisions. Here you see star formation, and our mathematical modeling helps to analyze various hypotheses of star formation. A starburst is an astrophysical process that involves star formation occurring at a rate that is large compared to the rate that is typically observed. This starburst activity will consume the available interstellar gas supply over a time span that is much shorter than the lifetime of the galaxy. The model of equilibrium hydrogen chemokinetic was also used in this simulation. Due to the high amount of star formation, a starburst is usually accompanied by much higher gas pressure and a larger ratio of hydrogen cyanide to carbon monoxide emission lines that are usually observed. The problems of astrophysics differ from the usual problems on a huge scale. Distances are measured in parsecs, and masses are measured in the mass of the sun. Here we see mass of the sun. We reduce the equations to a dimensionless form. When we solve our system of equations on a computer, all our close to 1. And when we analyzed the results, we multiply our calculated values by these basic quantities. Currently, there are 2 main approaches to solving problems of gravitational gas dynamics. First is Lagrangian SPH approach, smooth particle hydrodynamics approach, and AMR approach, adaptive mesh refinement method. SPH is a group of methods that models gas as moving, interacting particles. This method was developed for modeling solids, and there is no grid in this method. But there is a region around each particle within which all the particles affect this particle. AMR is a method that is based on the Godunov method. I told you about this method yesterday. Not about this method, about academician Godunov. This method is based on the property of the solution to move along the characteristics. The Godunov method is the most famous method for solving gas dynamic equations in the world. I told you about it at the first lecture. Why am I talking about an approach and not about method? Because there are so many variations of these methods. They are united only by a common principle. These approaches have their advantages and disadvantages. You can see it on the slide. Therefore, everyone chooses their own approach to their tasks. This slide shows the basic works where you can read more about these approaches. And I had a big article in Russian language on this topic in 10 years ago in Russian journal. Our code fluids in cells method. This method is not particle method. It is the method by Bielak-Tsiolkovsky. This method consists of two stages which are based on splitting by physical processes. At the first Euler stage, the gas is considered stationary. We have know this part. The system of Euler stage equations is obtained from the original system of equations if they omit these divergent terms of the density of mass flows, the component of momentum and energy. Then Lagrangian stage here. This system of Lagrangian stage equations contains divergent terms and is responsible for the process of advective transfer of gas dynamic quantities. Here you can see it figures. At the second Lagrangian stage of the scheme, transfer effects are calculated, taking into account the exchange between cells when they are rebuilt to the previous Euler grid. At each time step, the solution of the continuity, motion, and energy equations is reduced to a sequential implementations of the Euler and Lagrangian stages. As the initial condition for the Eulerian phase takes the value functions from the previous time step for the Lagrangian initial condition is the solution of the Euler stage. Over time, the mass flows pass through the boundaries of Euler cells determined by the grid step H. In this case, it is assumed that the entire mass is transferred only due to the normal velocity component to the boundary. At this stage, the unknown values, density, momentum, and specific energy are determined at the Euler stage. We use the Godunov type scheme. Also, the velocity correction is employed at the Lagrangian stage. Minimized. Also, the velocity correction is employed at the Lagrangian stage, and energy imbalance is minimized. Let's look at our system of gas dynamic equation. Here we calculate kinetic energy, internal energy, and total energy. Okay. We know that the total energy is equal to the sum of the kinetic and internal energy. In the process of calculations, this is not this is this is not always accurately performed in the process of calculations. If we test this, we can improve our solution. The renormalization of the velocity vector length, its direction remaining the same on the boundary gas to vacuum. The entropy or internal energy correction on regular density and such a modification of the method keeps the detailed energy balance and entropy non-decrease guarantee. Again, we do renormalization of the velocity vector length, but its direction remaining the same. And then we do correction of internal energy. What we do here. There are many difficulties of solving this problem in this modeling. The slide shows so-called carbuncle effect. What is this? What is carbuncle effect? This is the absence of rotational invariance. In the calculation, the gas is moving faster along coordinate lines. You see it here. For example, when the time is spread evenly in all directions, we get a gas vacuum boundary instead of a circle. We get a rhombus. To get rid of it, we had to improve our algorithm. Checking the correct solution is especially important for astrophysics problem. We have observational data, but we don't have precisely measured quantities or repeated experiments. And here in this slide, you can see a very long list of tests. This is example of the test, of the simple test. But we have only 5 minutes, so I want to tell you about parallel implementation. At each stage, the computational domain of this size is divided along zero x-axis into layers, and layers have this size. P is the number of processors. Now it is not pressure. Domain decomposition at the aileron stage is performed with one layer overlapping. One layer is enough because the central difference operator is used for derivative approximation. Flick method is a difficult one for an efficient parallel implementation. SPH method will be better in parallel implementation. And one of the main questions is the proper distribution of grid arrays between processor elements. In order to create parallel implementation of this method, domain decomposition technique was chosen. And here we see this method has 4 stages: aileron stage, Poisson equation, Lagrangian stage, and here we see time for each stage. And now go to the summary. The numerical method. We choose the high order low dissipation numerical solution. We study some information. Here some information about dissipation at last lecture. Not using of artificial viscosity or limiters. And the Galilean invariant of numerical solution. Entropy non-decrease guarantee, regular procedure for extension on other numerical models. simplicity of parallel implementation of hybrid and classic supercomputers, and potential infinity scalability. This the summary of our work in this project. So thank you for your attention. If you like this topic, you can join to our group in Riemann University. And now I can answer your questions. Thank you.
Thank you very much for the interesting lecture, and we have some questions. The first one is, you assume that the mass of stars equals the mass of gas. Does it correspond to the astrophysical observations? And have you studied the case where they are different?
Yes, now my colleague Igor Kulikov in Novosibirsk do this work. In this slide, you can see the case when mass of a gas is not equal to mass of gas in two galaxies. It is not the same masses of gas in two galaxies. Also, we can do calculations with mass of gas greater or less than mass of central body. And this case, when the mass of gas and mass of central body is equal, it is very easy model. And in astrophysics, it is very important to have easy model because astrophysics want to see the pure result of pure effects of this collision. Okay.
Thank you. And the last question is the following. For the calculation you have shown, it would be better to use a cylindrical coordinate system. That would solve all the problems. Why do you solve this problem on a rectangular calculation grid?
Mm-hmm. Rectangular calculation grid. Give me a moment. You can just a moment. I have some problems. It will be better to use cylindrical system of coordinate system, and we can get our solution, but our model is for for many other models for different problems. Our grid, our calculation grid is equal for the whole domain, calculation domain, and we can do our calculations with equal точность.
Accuracy.
Accuracy. Oh, okay. And galaxies can just a moment. Galaxies can collision not by pairs. It can collision 5 galaxies or 7 galaxies, and we can calculate these scenarios too. So our model is more universal for any problems. That's all.
Thank you. Thank you. Thank you again for the interesting mini course, and thank you for your answers. Dear listeners, a break is announced until 1 p.m. in Moscow time. Thank you.
Hello?
Good afternoon. Can
Oh,
I
hi.
wait till 1 p.m., please?
Yeah, so I tried to answer your message. Now I can do it. Okay. But then I did not see the little window where I can answer you. So, okay, now I sent the message to you also.
I noticed. Thank you.
Sure, you're welcome.
Good afternoon, dear colleagues. We are going to start the last lecture of mini-cars of differential equations with state-dependent delays, some theory, new phenomena, and applications. And our lecturer is Professor Hans-Otto Walter, Professor of Justus Liebig University. So, Professor Walter, I can see your lecture, and you're welcome.
Okay, so thank you very much for the introduction. Now I go full screen. Just a second. You. Okay. Okay, now we can begin. So this last lecture will be a case study, and the aim is to understand again the effect, the impact of a state-dependent delay. So we shall begin with a very simple delay differential equation with a constant delay. And then we shall make the delay state-dependent. First, only a little bit. And what we would like to understand is what are the first changes which we see? What are the effects of introducing this state-dependent delay? So what I'm going to tell you is based on a PhD thesis, the dissertation of Therese Moore-Vogt, and also on some joint work with her. So we begin with this equation which you see here. The g is only a real function, the delay is 1, g is odd, continuously differentiable, here you see it. In particular, the g is constant on long intervals from -infinity to -b. Think of b as being something like 1/3 or so. And then it's decreasing, it's 0 as 0 because it's odd, and you see how it has to continue then for positive arguments. That's our starting differential equation. Again, we have to introduce some state spaces on which the semi-flows given by the solutions of the differential equations live, the space of continuous functions and the space of continuously differentiable functions. Notice that as the interval on which the solution segments and the initial values are defined is not the interval from -1 to 0. That would be sufficient if we would like to study equation number 1 alone. But we want to have some freedom. So this is why we consider initial data and segments which are defined on a little longer interval from -2 to 0. And then the equation is so simple that one can explicitly compute a periodic solution. The method follows, well, it's an old idea, it follows something which is in one of these monographs on retarded functional differential equations. And what we shall find is a periodic solution which first of all has a certain symmetry. P at t plus 2 is always equal to -p of t. So the minimal period of the periodic solution is 4. And then just due to the differential equation, the periodic solution will be twice continuously differentiable. Now here you see a figure which also explains how we can compute the periodic solution. And let's spend a little bit of time to see how this goes. You see, we start with an initial function phi. You see that in blue on the lower left corner of the figure, and that's defined on the interval from -2 to 0, but it's only important what phi does on the smaller interval from -1 to 0. And notice that between -1 and -b, the phi is below the level -b. This is where the g is constant and has the value +1. And then between -b and 0, the phi is the identity, the diagonal. Yeah. And now see what happens. If we take a t, we want to compute the solution using the differential equation. For t between 0 and 1 -b, the t minus 1 is between -1 and -b. But there, the right-hand side of the differential equation is given by phi at t minus 1, and the phi is below -b. That means our nonlinearity g is +1. So the solution on the interval from 0 to 1 -b has slope +1, so it continues as a straight line. And this is what you see, this is the black line, the solution. But now our solution is given by the identity between -b and 1 -b. That's an interval of length 1. And because the delay in the equation is 1, now this determines how the solution looks for t larger than -b up to +infinity. And then you can go piece by piece. For example, if you, in order to compute the solution, if t is between 1 -b and 1 +b, yeah, then the right-hand side of our differential equation, g of x of t minus 1, the t-1 is between minus b and plus b, there the solution at t-1 is just t-1. So we only have to integrate this. Yeah, and this gives us the solution between 1 minus 1 and 1 plus b and so on. And the result is what you see there. Yeah, and now, of course, you can continue up to infinity. You can also replace the phi by the piece of the solution between, let's say, between 2 and 4 and extend to minus infinity by putting together all these pieces, and you end up with a sad periodic solution. This process of computation of the solution also indicates that the solution, the orbit of the solution in the space C, must be very, very stable. For example, one can show if one starts close enough to the periodic solution with some phi close to this O in the space C, then the corresponding solution merges into the periodic orbit. After some time, the other solution becomes the same. It's the same as a shifted copy of the periodic solution. Solutions flow together. So this is much more than exponential attraction as you would usually have in stability or so, or attraction. So it's much better. So you have merging in finite time. Now this periodic function P, which we obtained as a periodic solution of this initial delay differential equation, also solves many other delay differential equations. Of course, every delay differential equation with a state-dependent delay, look at the d here now in the equation, where the d along the segments of the periodic function is 1. Now, in our situation, we can write down delay functionals d which do have this property that along the periodic solution, along the segments of the periodic solutions, the d always is 1. Namely, look at this. Take a d of the form 1. Oh, sorry, I have to go back. Which is 1 plus some rho. Rho is a real function which has values between -1 and +1. And the rho has the property that at 0, it is 0. Now look, because of the symmetry of the periodic solution, the segments p sub t have the property that p sub t at 0 plus p sub t at -2, this is always 0. So along the periodic solution, if we have such a functional delay functional d, this is always 0 and only the 1 remains. Yeah. So in particular, our periodic function solves every equation with a state-dependent delay of this form. Now we do not want to study one particular state-dependent delay of that form. I told you we want to learn something about the onsets, the beginning of the effects of the state-dependent delay. So we would like to replace this rho by a one-parameter family of functions with such properties. And these, now we replace the one function rho by the one parameter family delta. The second argument of the little delta, that's the capital delta, that's the parameter which we are going to have. And the first argument, this is just the variable. Now here we require that the delta, if the parameter is 0, then it's identically 0, which means the delay functional given by 1 plus delta, this is always 1 everywhere. So for parameter delta equals 0, we will have our original equation with a constant delay. And the second property is just what I told you, which means if we have along the solution the symmetry, then the delta also is 0 for arbitrary delta. And then we get that along the periodic function, the delay is 1. And then the third property is that this delta is not identically 0. It means if we have a small delta, then the derivative with respect to the first variable, this is delta. So for delta equals 0, it's 0, of course. But if delta is non-zero and small, we have a little slope. And that means the delta does depend on the x's, a little bit at least. Here you see examples. If you take sine of xi times delta or hyperbolic tangent of xi times delta, they fulfill these properties. And then here you see again what I mentioned just a few seconds ago. Then we define delay functionals depending on delta by this formula which you see here. And then, as I just tried to explain, we have that along this particular periodic function, if you look at the segments, then the d sub delta at such segments equals 1 everywhere. So our fixed periodic function satisfies this equation number 2 with the parameter delta. And then, as I said to you, for delta equals 0, equation 2 reduces to equation number 1. If delta is non-zero, we do have a state-dependent contribution to the time lag, not along the periodic orbit, but perhaps at other arguments, at other states. Well, all these things, they are done in such a way that one can apply this theory, which I talked about in the first lecture and which I mentioned also in the second lecture. So we get this so-called solution manifold, which is given by this compatibility condition, which you saw before in the space C1, continuously differentiable functions. And on that manifold, our initial value problem for equation number 2 is well posed. And if we look at the semi-flow and at the solution operators S sub delta, then the solution operators are all continuously differentiable. They assign to every initial function or value phi in the solution manifold the corresponding solution at time t for a given fixed t. So they map a part of the manifold into itself. Now back to our periodic function, which is a solution to the equation number 2 for arbitrary delta. So the initial value or initial function pi naught, pi on the interval from -2 to 0, that is a fixed point of the period map, which is given by time t equal the period of p, which is 4. Yeah. So this is for arbitrary delta. We have these fixed points. And now, what sort of impact of effect due to state-dependent delay are we interested in? Well, that's stability. And it's stability on the level of linearization, so which may be called linear stability properties of the periodic orbit O. O seen as, or with respect to equation number 2, with respect to other solutions of equation number 2. Or in other words, we could also, which is almost equivalent, we could also ask for linear stability properties of the fixed point P naught of the period map S delta, 4. Well, these linear stabilities, they are by definition, if you want, or by convention, they are the spectral properties of the so-called monotony operator. This is nothing but the derivative of the period 4 map at its fixed point, the linearized period map. And now remember, as the period map, like all solution operators, maps the solution manifold or part of it into itself, the derivative at a particular point, like at P naught here, maps the tangent space at P naught of the solution manifold into, in general, the tangent space of X delta at, let's say, S delta of 4 of P naught, but this is because this is a fixed point, it is again P naught. Yeah, so the monotony operator takes this tangent space into itself. Now, how do the spectral properties of the monotony operator affect the stability of the periodic orbit? Just to mention one example. If we have at least one eigenvalue which is larger than 1 outside the unit circle of the monotony operator, then it follows that the periodic orbit is unstable. Just to show you one relation between spectral properties of the monotony operator and stability properties of the periodic orbit. And our objective now is to describe the spectrum sigma delta of the monotony operator for every parameter capital delta. Now I have to say a few more words. How could we come closer to this objective? First of all, here you see again the formula, the monodromy operator, like in general derivatives of solution operator, is given by solutions of a variational equation. That's the differential equation which you see in the second line from the bottom. V prime of t equal derivative of f delta at pt applied to vt. Now what is the f delta? This is just the nonlinear functional on the whole space C1, which represents the right-hand side of our equation number 2. At the bottom here you see the formula. And then you see this variational equation, and the initial data for the solutions of the variational equation, which describe the monodromy operator, they of course are taken from the domain of the monodromy operator only, from their tangent space. The x's are in the t sub p naught of x delta. Okay. Well, one general fact, which is, well, the same as you would have it in ordinary differential equations. If you differentiate the equation number 2 for the periodic solution, then you see immediately that the derivative, p was twice continuous differential, remember that, solves the variational equation along p. And that means, as p is periodic, also the derivative is, you have p prime, the segment at time 0, is the same at p prime, the segment at time 4, but this by definition is the value of the monodromy operator at p prime at 0, and that means the number 1 is an eigenvalue of the monodromy operator for every parameter delta, and p prime, segment at time 0, is one eigenvector of that eigenvector, as always. Now computing the derivative in this variational equation, this is easy to do. We get a more explicit form of the variational equation in terms of the g and of the derivative of the delay functional delta, and this is what you see in the equation number 3. You see the g prime at p of t minus 1 multiplies something in brackets. Also on the right hand side you see the parameter delta, that is the only left over from differentiating our delay functional. Now notice that something is very nice and very simple about this variational equation, namely because of this factor g prime at p at t minus 1, the v prime of t, for every solution of this variational equation, this is 0 on certain intervals. And that means the v itself is constant on certain intervals. We know that a priori. For example, if t is between 0 and 1 minus b, then the argument of the coefficient, the p at t minus 1, t minus 1 is between minus 1 and minus b, and there the p is below the level minus b, and below the level minus b the g is constant, so the derivative is 0. Yeah. So in that interval the v prime is 0 and v is constant, and similar for the other intervals. The long interval from 1 plus b passing 2 until 3 minus b, on that interval the v must be constant, and again on the interval from 3 plus b to 4. So only on these little intervals between 1 minus b and 1 plus b, and 3 minus b and 3 plus b, and of course copies of intervals to the right and left, the v is possibly non-constant. Well, another implication of this observation is the following. Let's have a look at this tangent space on which our monodromy operator is defined. Well, here in the second line from the bottom, you see again the characterization of this tangent space, the general thing, by a compatibility condition which involves the variational equation. And again, you see this factor g prime evaluated at p at minus 1, but at p minus 1, the p is below the level minus b, and this is where the derivative of g is 0. So you see this tangent space is simply given by the condition derivative of xi at 0 is 0. So that's a closed hyperplane in the space C1, and let's call that y, and in particular no parameter delta is visible anymore. All domains for all monotony operators, they are all the same. And this, of course, at least from a technical point of view, that facilitates the study of the monotony operators. They live all on the same space. Something else, let me remind you, I would like to talk about the spectrum. That the spectrum of an operator that in general is defined for operators on complex vector spaces. So also here, the spectrum sigma sub delta, by definition, is the spectrum of the formal so-called complexification of the monotony operator on that real Banach space Y. Now in our situation, if we really would work with a formal complexification, that would be a little bit unpleasant, simply for formal reasons. We would have to write down always pairs of things and so on. That's not very nice. But this complexification here, in fact, is conjugate to the following operator, which we may take for the complexification. This is script m with the argument delta, which lives on the space script y, and here it's given by the segment at time 4 of the complex valued solution of the variational equation given by complex initial data taken from script y, which is nothing but the analog of the y which you saw before. It's the complex valued continuous differential functions on the interval from -2 to 0, which have derivative 0 at 0. So this script m delta, this will be and the spectrum of that will be the object of our study. Now, the first thing to observe is that all of these operators, they are compact, and that of course means their spectra are at most countable. Away from 0, they consist of isolated points, which are all eigenvalues, and their geometric and algebraic multiplicities are all finite. Now let's go back in terms of this framework which I just talked about. Let's have a look back to the initial situation, the equation with constant delay, which is now the case parameter capital delta equal to 0. Then we can play around with the variational equation for delta equals 0, and it's not very difficult to get the following result. The whole spectrum of the monotony operator for delta equals 0 consists only of the numbers 0 and 1. 1 is always there, as I mentioned a few minutes ago, and 1 is a simple eigenvalue, meaning that the algebraic multiplicity equal to the geometric multiplicity is 1 one-dimensional eigenspace, and then the number 0, which belongs to the spectrum, which in general for compact operators is not necessarily an eigenvalue, but here it is. And then we have the direct sum decomposition of our domain of the monotony operator, which you see here. At the right-hand side, you see the complex multiples of the eigenvector p prime segment at 0, this one-dimensional eigenspace, and before you see the kernel of the monotony operator. But here the kernel is nothing but the geometric eigenspace of the eigenvalue 0. So we have a decomposition in a space of codimension 1, the eigenspace, yeah, and then you have this one-dimensional complement. Now you see, for here in the eigenspace is the kernel. So at time 4, the solution of the variational equation is 0. We are in the eigenspace. So all solutions of the variational equation which start in the eigenspace become 0 at time 4, and of course afterwards they remain equal to 0. And that reflects on the level of the linearization this kind of extreme attraction, this merging into the periodic O for the solutions of the nonlinear equation. Yeah, this is reflected by this direct sum decomposition which you see here for the linear objects. Well, how about eigenvalues for parameters which are non-zero? Yeah. Then our variational equation is not so simple anymore, and actually there one has to work quite a bit more in order to find out something. First of all, and this is not so difficult, one can prove what may be called a continuity result. If we take for parameter non-zero the spectrum, but without this eigenvalue 1, which always is present, then the remaining spectrum, this set of points, tends to the singleton, which only consists of 0, as delta, the parameter, goes to 0. Now, due to this very strong stability which we have for parameter 0, any effect of introducing of a beginning of variability of a delay, of state-dependent delay, in our situation can only be some kind of destabilization of the periodic orbit, now with respect to the solutions of the equation number 2 with the parameter delta. Yeah, this is a consequence of the situation which we began to study. But how does this happen? For example, one possibility would be that the eigenvalue 1, that the eigenvalue 0, which has this large eigenspace of codimension 1, that is no longer semi-simple, so that the algebraic and geometric multiplicities are no longer the same for delta, non-zero, and close to 0. While actually this is not what's going to happen, but that's a possibility which actually happens in other examples. Anyway, let's return to our problem. Now the tool which helps us to find out something about the spectra of the monotony operators for capital delta non-zero is a characteristic equation for these so-called Floquet multipliers. Here we can use a method which originated many years ago in the 1980s, and which later on always has been used by joint work with Professor Skubachevsky in a series of papers. And here again we can make use of that method. And now I would like to spend a little bit of time to show you how one can derive a characteristic equation for these Floquet multipliers. Now assume we have an eigenvalue, lambda, and we have an eigenvector, xi, which is of course non-zero, of this complexified monotony operator. So xi is in this space script y. Well, we rewrite this eigenvalue-eigenvector relation using the solution of the variational equation with parameter delta, which starts at xi. And then this eigenvalue equation results in the equation that the segment of v at time 4 is lambda times the segment of v at 0, which is the xi, of course. And we want to exploit this brief relation. Now remember that the v is constant on certain intervals, so it's not of much importance what the v does on these intervals. So let's introduce maps u and w, which live on the small interval from -b to b, complex valued. They are given by shifted restrictions of the v. For example, the u is the v on the interval from 3 - b to 3 + b, shifted back to this little interval from -b to b. And similarly, the w is the v on the interval from 1 - b to 1 + b, shifted to this interval to -b to b. Now we try to arrive differential equations, for a system of differential equations for the u and the w. Also, we have a boundary condition. You see the u at -b is the v at 3 - b, but v is constant between 1 + b and 3 - b. So this is the same of v at 1 + b, and this is w of b. So here you see the beginning of a set of boundary conditions for u and w. Now let's begin with the differential equation for u. So the u prime of t is the v prime of 3 + t. And then what you see here is just the right-hand side of the variational equation, and the argument is not t but 3 + t. Nothing else, it's just copied. But remember, here you see v of 3 + t - 1, so it's v of 2 + t, and t is between -b and b, so we are close to 2, and this is where v is constant. So the v is the same as the value of v at 3 - b, but this is u at -b, so this is why this comes in. And then here we had the v at 3 plus t. This is already replaced by a u. You see that here also. Here you see 3 minus 2 is v at 1 plus t. This is w. And here you see p of t plus 2. That's the same as here, but using the symmetry and the fact that g is odd and the derivative is even, this is p of t. Sorry. But t is between minus b and b, and there p is the identity, so this is just t. So this is a differential equation for u. But notice here it contains not only the value of u at time t, as it would be the case in an ordinary differential equation, it's u at minus b. Yeah, it's, if you wish, the initial value of u. So formally, the differential equation we get is not an ordinary differential equation. It's an equation of Volterra type. In general, you would have an integral, but here it's an integral with a delta function, and it reproduces the initial value. Okay, now let's continue. And now, only for t between 0 and plus b, let's derive a differential equation for the w. This is just done in the same way. W was v at 1 plus t. Here you see the right-hand side of the variational equation at 1 plus t. Here we have already v of 1 plus t replaced by a w. And here again, by this, here this is v of t. T is between minus b, no, between 0 and plus b. But there the w is constant. It's the same as w at 1 minus b, but this is w of minus b. So this is why this comes in. And here, yeah, this is v at t minus 1. Now there's something new comes into play. Now we use the relation that we have the segment of v at time 4 is lambda times the segment of t at 0. T minus 1 is between minus 2 and 0, and t plus 3 is between 4 minus 2 and 4. So we can use this relation, and then we can replace this by 1 over lambda. Now the lambda comes in. Sorry again. So we get here this with a v at t plus 3, but this was u. Okay. And then the same thing here. This is just g prime at t. And here the t is between minus b and b. There p was identity, the derivative is 1. So this is our equation for, sorry, w. And it's again of the same type as the equation for u, only now it contains the parameter lambda, and it's of this Volterra type. Well, let's rewrite this as a system for u and w. Here we have a matrix, and the matrix is just g prime of t times the parameter delta, and these are scalars, but here we have a matrix, just this one. And then we have the other term, g prime of t, multiplied by u and w evaluated at minus b. Let me just call this c. So formally, this looks like a linear inhomogeneous ordinary differential equation with a certain parameter c, which you see here. Also, we get a boundary condition. I explained a part of u. I showed you that u at minus b is the same at this multiplied by that, the w of b. And one also gets this, the rest here. Let me use this in a minute. Now let me think of the linear part of the former inhomogeneous linear ODE, which you saw. For the linear part, because the matrices have this special form, they commute for arbitrary time argument s, and that means a fundamental matrix can be computed. It's of this form, everybody knows that, and carrying out the integration, we get this as a result for the fundamental matrix. And now we are still after the characteristic equation, don't forget that. Now we use this relation, that the c, the uw at minus b equals this. And in that relation, we use the variation of constants formula for the linear inhomogeneous ODE with the parameter c in order to replace uw at time b, well, using the variation of constants. And this is what you see here. Here you have the c, this is this product, which you see up here, and this is replaced by this bracket here. Here you have the fundamental solution at time b, evaluated at the initial value. This is C UW, sorry, at minus B, and this comes from the inhomogeneity, which in our case also contains the C. So the result is, okay, I should add something else. We started with an eigenvector here, which was non-zero. Then it's easy to see that the UW, this pair of functions, is not zero. And then it follows, it's also easy to see that our initial value for the UW cannot be zero. But that means the C is not zero. And here you see it satisfies a matrix equation. Yeah, this matrix equation has a non-trivial solution. I don't give you the formula for that because it's just too long for now. But this is what is the characteristic equation. The determinant of this matrix must vanish. And that depends on lambda and the parameter capital delta. This is the characteristic equation. I showed you how to derive it. One can also go back. One gets a characterization. If lambda is a non-zero complex number, then it's in the spectrum sigma delta. It's an eigenvalue if and only if this determinant vanishes. What one can also do, using the same ideas but in a more complicated situation, one can compute the resolvents of the complexified monotomy operator. These are the inverse mappings for parameter lambda and the resolvent set, which is the complement of the spectrum. There these maps exist, and one get formulas for these resolvents by taking some eta in the space script y and trying to compute the solution of this equation. So the he is the pre-image. Yeah, so it's the value of the inverse. See, if eta would be zero and if the lambda would be an eigenvalue, so not in the resolvent set, then this is just what we did or could have done when we try to derive the characteristic equation. So now it's only a little bit more complicated. The basic equation is this one, where the right-hand side is not equal to zero. The formula for the resolvents is important for the following. We are not only interested in the spectrum and the eigenvalues of the monotomy operators, which are the zeros, the solutions of the characteristic equation, but we are also interested in the multiplicities of these eigenvalues. And these multiplicities, they are related to the orders of the eigenvalues. The eigenvalues are poles of the resolvent map. And the order of the poles is related to the algebraic multiplicities, actually to the chain length, but anyway, of lambda as an eigenvalue. So we need that also. Now, this form of the characteristic equation with this complicated matrix, which involves the fundamental matrix solution of a linear equation and so on, this is not immediately suited for working with it. So it's not really trivial to bring this characteristic equation in a practical form, which can be used. And this is what you see here. If we have a complex number which is not 0 or 1, and if the parameter is not 0, then one can actually explicitly compute the characteristic function, which determines the characteristic equation. And it's of this form. See here these abbreviations. This is the hyperbolic cosine evaluated at, well, sorry, that's square root 1 over lambda minus 1. Here you have the imaginary unit. Here you have the parameter. Here this capital SH, sorry, this is just an abbreviation for the hyperbolic sine evaluated the same argument. And here you see the right-hand side. Yeah. It's easy to see that there's a certain symmetry. It's the same if you take delta or minus delta. So we look at zeros of the characteristic equation only for delta parameters capital delta non-negative. And this is what we shall do. Now let me now do this. This, of course, some work has to be done. And here are the results which I would like to present you. First of all, if the parameter delta is 0, then I mentioned that the eigenvalue 1 of the monotomy operator is simple. So the algebraic multiplicity is 1, but this is true for all parameters delta. It's always simple. Next, for delta between 0 and plus infinity, there exists exactly one eigenvalue which is new now, which is negative. Well, look at the mistake. Here it should have been a strict inequality, because if delta is equal 0, then there is no negative eigenvalue. Then there are only the eigenvalues 0 and 1. So excuse me for that mistake. That should be a strict inequality. But we have this unique eigenvalue, and the unique eigenvalue has a negative derivative with respect to the parameter. That means if you follow the eigenvalue, you vary the delta from 0 to plus infinity, then you see that this negative value is decreasing, strictly decreasing. Furthermore, one can show if you let delta, which is now positive but goes to 0, then one can show that this negative eigenvalue increases to 0. In other words, we have a bifurcation in the Floquet spectrum from the eigenvalue 0, delta equal to 0. Yeah? This negative eigenvalue bifurcates away from the eigenvalue 0. And furthermore, one can also show if delta goes to plus infinity, when the eigenvalue lambda is negative and decreasing, that actually it goes to minus infinity. That means in particular there must be exactly one parameter, delta star, at which this negative eigenvalue crosses the unit circle at -1. And if delta is larger, then this negative eigenvalue is less than -1, and that means the periodic orbit is unstable, actually. So that we do get. What else? Next, at the parameter where the negative eigenvalue equals -1, there the algebraic multiplicity is -1. And this is something which is important or crucial for a bifurcation from the periodic orbit in our, given by the solution of the nonlinear equation, namely there occurs a so-called period doubling bifurcation at this critical parameter. What is that? That means that if I look at the periodic orbit considered or given by the periodic solution of the equation number 2 with parameter delta star, and I look at the neighborhood of this periodic orbit, then for delta, capital delta close to delta star, then this neighborhood, the small neighborhood of this periodic orbit contains the orbit of another periodic orbit, of another periodic solution of the equation with parameter delta close to delta star. And this other periodic solution has a period, a minimal period, which is close to two times the orbit of our always considered periodic solution 4, so it's close to 8. So this is period doubling. And this comes responsible for that is that an eigenvalue crosses the unit circle at -1. And what you see here, these properties 1, 3, 4, and 5 combined, they guarantee that all the hypotheses for period doubling on the level of the linearization, that they are all satisfied. In order to really prove that a period doubling occurs, one has to work with the nonlinear equations, and this is a little bit more, which has not yet been done, but I think it's a kind of routine to carry out even these details. Furthermore, there are no eigenvalues for no parameter between 0 and plus infinity. For any parameter, there are no eigenvalues, real parameters larger than 1. Well, so far, no results about non-real eigenvalues. How is it with non-real eigenvalues? Well, if one tries to find eigenvalues for certain parameters delta between 0 and 1, this was also missing up to here, then one sees there is a sequence of critical parameters delta k, all positive, going to plus infinity if k increases, such that at these critical parameters we have a double multiplicity 2, of the zero of the characteristic equation, a double eigenvalue lambda k between 0 and 1. And these double eigenvalues, if you look at them for different parameters, then they are increasing, by the way. But let's stay with one critical parameter, delta k. What happens to the double eigenvalue if I increase delta? Well, then lambda k bifurcates into a pair of simple real eigenvalues in this interval between 0 and 1. And if I follow them for delta going to plus infinity, then both these now simple real eigenvalues converge to plus 1. Yeah. What happens if I take delta a little bit smaller than the critical parameter delta k? Well, then these double real eigenvalue lambda k bifurcates into a pair of simple complex conjugate eigenvalues. So here we have some non-real eigenvalues. But what could not yet be done is a complete analysis of all the non-real eigenvalues. Of course, we have this result that if delta goes to 0, that then the whole spectrum, except 1, goes to 0. That tells us something about possible non-real eigenvalues, of course. And a conjecture is, of course, that these bifurcating complex eigenvalues, that as delta goes to 0, I make it smaller, that they just go to 0 and that there are no further ones. But this has not yet been proved, and there are no numerical results which indicate that there are further complex non-real eigenvalues. Okay, let me close. My time is over anyway, with a few problems which remain. Well, this is this description of all non-real eigenvalues. In particular, could there be pairs of complex conjugate eigenvalues which, if delta is varied, cross the unit circle? That would imply that there are also other bifurcations, perhaps from the periodic solution, from the periodic orbit into invariant tori or so. I do not think that this happens here, but we cannot yet exclude it. Then, of course, some homework, carrying out all the details of the pair doubling bifurcation. For example, one little aspect of it, this is you would have to treat the pair doubling as a bifurcation of fixed points into orbits of length 2 of a Poincare return map. But all of these return maps, which you would have to consider for different parameters delta, they live in different manifolds. Yeah, so you have to develop some nice framework to do all that. Another thing is, remember that in our situation, the state-dependent delay resulted in destabilization of the periodic orbit if the parameter is varied. But of course, one is maybe even more interested in examples where a state-dependent delay helps to stabilize an unstable periodic orbit. And in principle, one could try to do this too. One would have to start with another example where you have a periodic orbit, which you can explicitly compute, but which is unstable for the equation from which one starts. Yeah? And then the ultimate goal perhaps would be to find criteria on the state-dependent delay, which properties are responsible for stabilization of a periodic orbit, which ones for destabilization. That would be nice to know, but this is still far away. There would be much work would have to be done in order to come closer to that. So thank you for listening, for your attention. This was the end of the lecture.
Thank you for your lecture. So there is no question. Seems like everything is clear, or maybe more real, that it takes time to assimilate information.
Yeah,
but,
yeah.
Yes. So anyway, I would like to remind that to listeners and lecturers that first of all, for next 4 lectures, you need to use another link, which you can find in program. And also we have discussions at 7 p.m. Also use link in program. And I would like to remind also about closing our workshop, because we have the last day and closing ceremony or something like this online will be at 8 p.m. Moscow time. So thank you again, Professor Walter, for interesting
Yeah.
lectures.
Yeah, thank you very much, and maybe see you later today.
See you later. Have a nice day. Now will be break for some time till 3 p.m.